Okay, so I'm very happy to introduce our speaker today. We have José Antonio Carrillo visiting us from Oxford. He's actually on a tour of the US. We're very lucky that he stopped by Santa Barbara on his grand tour. And today he's going to be speaking. I don't want to tease you. Anyway, I think sure. Unfortunately part of your title is cut off, but I believe you're speaking about non-local aggregation diffusion equations, fast diffusion, and partial concentration. So thank you again for that.
Thank you very much for the invitation here. It is always a pleasure to come to Santa Barbara. Lots of good friends here. So today I want to in fact report about a particular effect on aggregation diffusion equations. That's why a particular phenomenon that I want to focus is this partial concentration. So you will understand what I mean by that later on when I focus in the most specific part of my talk today. But at the beginning, especially for people that maybe not so well known, I mean that they don't know that much about aggregation diffusion equations. So I would like to introduce a bit the problem and also get to the fact of the fast diffusion problem and why that sounds interesting, explaining a little bit about something in between in the degenerate case to understand why this question becomes interesting. Okay, so first of all, and probably I don't have to explain too much in this slide for many people in the audience, but just to understand the kind of questions I want to focus, I introduce a bit the notation here. So let's say that we have M particles that are interacting through a pairwise potential that they denote by U. You have some pointer or something? Okay, that's fine. I use my finger. So so here essentially you have just the effect of that. I'm neglecting inertia, so and I have some kind of damping on the particles, so that's why I can write a kind of first order dynamics for the evolution of the particles. So I have xi dot equals the sum of the forces. So each particle at k is producing a force onto the particle at the location xi, which is given by gradient of the potentials. And somehow, if you want to write the easiest continuous model that corresponds to that kind of interaction, so you call. Thank you. Thank you. Yes, perfect. So if you denote by rho dx the density of particle at time t, then here you are just writing that the velocity field is generated by the density rho in the same way that here is done by particles. So each part of the mass produces some force of location x given by gradient of ux minus y, and you sum them up. So if this is the velocity field generated by the density, what you would expect for the evolution of the density in time is this kind of evolution, a kind of continuity equation where the velocity field is given by minus gradient of u convolved with rho. So of course, writing this is an interesting question that I don't want to discuss today, but that's the origin of that problem. To be a bit more general on the model that I want to discuss later on. So typically, when you have a potential, you are going to discuss both attractive and repulsive effects between the particles. And typically, what you can do is to separate in the potential a part which corresponds to the repulsive part of the potential, the part which is the attractive part of it. And under the assumption in which you
sorry about the previous
sure.
slide. You know, very stupid question. Why is x dot?
Yes, I mean, you start with Newton's law. I just neglecting inertia term. So you have damping, and some of the forces I'm neglecting inertia term. That's why I write it. So first order dynamics. Okay. So you separate somehow in the potential. Yeah, the potential U with two parts, let's say the attractive, the repulsive, and you scale the repulsive part in such a way that you make it very strongly concentrated at zero. So say that this guy you think about it as something like it's approximating a Dirac at zero with certain strength that you want, then you're gonna get to equations that have this blue part, kind of nonlinear diffusion part, which is kind of the modeling the repulsive effects in the potential view. So, I mean, just to make it more clear, you see if the general, I was saying before that the equation is rho t plus divergence of rho u equals 0, u equals minus the gradient of u combined with rho. So if you do this separation and then you keep as non-local just the attractive part of the potential and the repulsive part, you scale it like that. Essentially, when you put in the convolution the Dirac, you're going to get here minus epsilon gradient rho. Okay? Plus or minus epsilon. So let me see. Yes, this one. So if I write it like this, then you recover like porous medium equation with exponent 2. Porous medium equation with exponent 2, remember, is just corresponding to the fact that I have here divergence of rho gradient rho, which is essentially Laplace squared. Okay. So just summarizing, the question I want to discuss is under which assumptions on U and P you will have a balance between the attraction modeled by the non-local part and the repulsion modeled by the nonlinear diffusion. Okay, so that's the question. How I want to solve it. So let's think first about how to attack that kind of question. I mean, it's a bit philosophical to say the balance between these two mechanisms, but the fact is that that equation has a structure, has the structure of gradient flow. In fact, it has a Lyapunov functional, which has a lot of, I mean, it has a clear physical meaning. The first part of the free energy functional is the total potential energy generated by the density rho, because you combine with rho is the potential generated by the density rho multiplied by rho and integrated. The blue part, depending on the type of diffusion that you want to include, it's, well, in general, we can say it's the entropy, we can call it the entropy. In the case of linear diffusion, it's exactly Boltzmann entropy, rho of rho. And the interesting thing is that that equation, as I wrote it, has this general structure. So now I'm writing the equation I'm dealing with is like that. See, if I got the same, I wrote it like this, no? Correct? Yes. So so this equation, it can be written in this way. It can be written in the sense that this is minus the gradient of the variation of the energy that I'm writing there. The free energy, which is given by, I may write it over here for later purposes, the integral of u of rho multiplied by rho, plus the integral of some nonlinear function of rho, which is related to P by that relation over there. Okay? So then we can decide to say that the balance between attraction and repulsion happens when I'm able to find non-trivial local minimizers or global minimizers of the free energy. So I want to identify the different regimes and what are the properties of those potential local or global minimizers. So that's the question. There are a couple of particular examples that are well known in the literature and quite classical. Probably the first one, which is when you pose this question, but not at this level of densities, but just with Dirac deltas, when you talk about very singular potentials. You consider very singular potentials, say like Leonard-Jones type of potentials. Then this was treated in the 70s and the 80s, and is very much related to works in statistical mechanics for crystallization. And then probably the other particular case, and this one is quite far from this setting in the sense that it doesn't make sense when you have very similar potentials for talk about the free energy over densities. It doesn't make sense. But probably the most classical one in this setting is when you take U as the Newtonian potential. And that corresponds to classical models in math biology, like the Keller-Seeger model for chemotaxis, that also appears in astrophysics models for gravitational collapse. But probably also it's worth it to mention that there are several other applications, more modern applications of this. And this kind of question appears very naturally also for mean field gains when you talk about Cournot-Nash equilibria. It's very similar to this kind of issues. For fractional diffusions, when you have potentials more singular than the Newtonian, you can understand this as the inverse fractional Laplacian associated with the density rho. So certain particular cases of nonlinear, non-local fractional diffusions can be treated in this way. Finally, probably when you look at eigenvalue distributions of random matrices, you end up in particular cases of this problem. So just I have okay. So now what I would like to move is to a particular setting to try to understand the different regimes, which is the setting in which both the U and the P are homogeneous functions. So let me see what notation I have, and then I write it there. Okay, so yes, good. So I'm going to say that for the rest of the talk, always I will talk about the case in which P of rho is rho to the m. Well, in fact, with that notation is rho to the m minus 1, which I wrote. And the U is modulus of x to the k divided by k. Okay, I will explain now the ranges in which I'm considering here. M is a positive number for the time being. And what I'm going to say in this slide, k is larger than minus dimension. It can be also positive, and I will discuss that later. But in what I'm going to say right now, let's assume that k goes between minus dimension and 0. To simplify a bit, and when I say when k is 0, I'm just thinking about the logarithm. So it's just a notation to include also the Newtonian part. I mean the Newtonian potential into the U. I put also scalar here, chi, just to model, if you want, the different strength between attraction and repulsion that in some particular cases plays a role. And maybe in some slides later on, I'm normalizing the densities to a probability density, so such that the total income is 1, but maybe in some times not. Okay, so I will explain which ones I'm normalizing. But it doesn't really matter. The mass is conserved for that PD. In the cases I'm going to discuss, in fact. So just basically based on pure scaling arguments, you can easily realize that there should be at least these different cases based on the relation between M and K. How can you find that out? It's sort of easy, because now in the free energy, you will have something like this. Let me write it in full again now. Plus double integral 1/2 modulus of x minus y to the k divided by k. I put the kappa, the k here, so rho x rho y. So what you do is simply to take a given profile and you take dilations of it. So call this rho lambda x. And then look at what is the behavior in terms of lambda for f of rho lambda. And then if you just do because they are both homogeneous, you can find the relation of how this behaves on lambda, how this depends on lambda, and you can identify different regimes depending on the powers that you get. That leads you to that relation over here. So what happens when M is larger than 1 minus K over dimension? In that case, I call it diffusion dominated regime. And why I call it like that? Because when you squeeze the profile of the given density to become closer and closer to a delta, the free energy, in fact, increases. Okay? So then this tells you that it is more preferable for the energy, since the energy is decreasing, to spread the mass than to concentrate it. This doesn't mean that a priori is going to spread the mass like the heat equation all the time. I'm just saying that it's better energetically favorable to spread the mass. That's why I call it diffusion dominated regime. If M is less than D minus, so in the other case, 1 minus K over D, that I usually call it the aggregation dominated regime, because the opposite happens. When you squeeze it closer to a Dirac, the energy in fact increases. So then it's more favorable to you to concentrate. And finally, you have the case in which both of them scale, both terms scale in the same way, which is when you have equality, which I will write it over here. M equals 1 minus K over D, which I usually refer as the fair competition regime, in which both of them scale in the same way. And then the chi, the parameter chi, plays a role. And in fact, what you can show, in some particular cases, this was done before, not in reality, then you can find that there is a critical value of chi separating different behaviors. So we'll come back to that point in a second. Probably you have heard about the Keller-Segal model, the classical Keller-Segal model in 2 dimensions. So the classical Keller-Segal model in 2 dimensions is precisely in this case. This corresponds to D equals 2, K equals 0, M equals 1. Yep.
Just double check, the range of K is negative, right?
K is between minus minus D and 0. Yeah. So M is between 1 and 2.
I think that's a
In that case, I will come back to K positive later. Okay. So what happens in the fair competition regime? And this is just to give you an idea of the particular question I want to concentrate later, what is going to be for K positive, but just to understand, for you to understand a bit the different behaviors. For the fair competition regime, when you have this equality, in fact, let me just tell you the answer in 2 words. Essentially, well, more than 2, but very few words. Essentially, what happens is exactly the same as for the Keller-Segal model in 2D. So you can identify a critical chi. So this is exactly what happens in the Keller-Segal model in 2D. And I'm just referring to that, but essentially this is what is going to happen. So you can find a critical chi, IC, such that you have infinitely many minimizers for that only value. Below that, the free energy function is bounded below, but the infimum is not achieved. So there are no stationary states. And you have to rescale the problem in order to have steady states. So you have some similar solutions, in fact. So this one behaves more like the heat equation like thing, and or the Potts-Medium equation. And when chi is larger than chi c, you can show that the free energy is not bounded below, and in fact you can have a time go up for the evolution. So remember that that's the case for the fair competition case is when you have homogeneity. So your free energy is homogeneous with some store, which it has some implications. In fact, whenever K is extremely negative, in fact, has, for instance, the implication that all the stationary states and global minimizers, if they exist, they have 0 energy, just because of the homogeneous relation. Okay. Good. How do you prove that? I don't want you to read anything like this in here. Just to say one thing that how you find the critical chi. The critical chi is related to the sharp constant of certain Hartley-Lewis overlapping inequality. That's how you identify the different regimes and the critical value of chi. So in fact, what's the Hartley-Lewis overlapping inequality that is involved? So if you apply the classical HLS, that's this line over here. So you just apply the classical HLS for the double convolution with modulus of x to the k. So you just open the book of Lead and Loss. You see that then you have that this is less or equal than a constant times the norm of f in LP, norm of f in LQ, and you choose P equals Q equals that number, then you get that that inequality is true. But the thing that you do afterwards is this LP norm, that is with the exponent 2d over 2d plus k, you interpolate it between 1 and m, because believe me, that number is between 1 and m, that is the 1 minus k over d. And then what you get is this inequality that now in the right hand side you have the L1 norm of f and the L norm of f. And the interesting thing is that the sharp inequality for this inequality is different than from the classical HLS. So you can prove that in fact that's true, and you get this variant of the HLS with a different critical sharp constant, and that sharp constant gives you the chi-c. And why it gives you the chi-c? Because essentially here you see you have that term of the free energy, and here you have the LM norm of f to the m, which is nothing else than this part of the free energy. So it's just kind of, you just see from here a relation between the two terms with the L1 norm in between, which is conserved by the PD, so this is just a constant. So that's why this characterizes for you that chi. I will not enter into the proof of that because this is not what I wanted to do today, but just to tell you a little bit the information there. So all of this to tell you that when k is between minus dimension and 0, and m is larger than or equal than 1, we have, in fact, this kind of, it's a bit more complicated than that, but I want to simplify it a bit. We have this kind of three cases. We have the fair competition case, which is corresponding to that red line, straight red line, the diffusion dominated and the attraction dominated. Just a few words on this. What is known on diffusion dominated regime? So in fact, in this range, and I'm talking everything between for the singular kernels. What we know here is that no matter what the chi is, in fact, there are global minimizers. And so here is the case in which you always have a balance between the two effects, no matter what the chi is. In the fair competition regime is where you have this value, its critical value. And then below, you can have blow up scenarios. In fact, here, in terms of the free energy, in the blue part, the influence of the free energy is minus infinity. It's not bounded with that. Okay, good. So is it clear now, more or less? Now let me get to the question I want to discuss today. I want to discuss what happens then in this area. Is it true that this homogeneity business still plays a role or not? So what I mean is that what happens when m, now when k is positive, k larger than 0, let's say less than d, although this is then later, it's not that important. And which correspond, well, I mean, we can look at it at what happens for m between 0 and 1. You could look at what happens when m is larger than 1, 2 for this k, but that one is very easy. That one is always diffusion dominated, and a direct proof of calculus of variation plus decreasing rearrangement tells you that there are global minimizers. So it's almost just 3 lines proof here, this part of the diagram. So the interesting thing, or the interesting question that remained was what happens in this range. Okay, and let me explain you a couple of things that we have been able to understand. First of all, we saw that, in some sense, the diffusion can still win against the aggregation, even if you have K positive, but the regimes, in fact, that appears are completely different. And let me explain you why this is so. So first of all, what happens when M is less than 1? As you see, if you go for M less than 1 and K positive, the role of these two changes completely because 1 over M minus 1 here, so they flip the sign. Okay? And in fact, this already tells you that maybe it's a good idea to find inequalities which are in the other direction. So the first thing that we look at, is there any inequality of the type of a reverse HLS inequality? Meaning that instead of controlling, the double convolution by LP norms, you do the opposite. You control some integral of a power of the density in terms of this double convolution. Well, I will refer to this like LM, but this is just a notation. Okay, it's just a notation when M is between 0 and 1, it's just to simplify my life. So if you see a row in LM, I don't know, I just refer that the integral row M is finite. So the kind of inequality that you would like to have is to control this one in terms of now this kind of double convolution, or I will refer to it as a kind of non-local moment, because at the end of the day, K is positive now. So the double integral of x minus y to the K positive for x y. And in fact, when we check on the literature, at that point, there was one example of this inequality for a very particular exponent of M and K. There was one relation between M and K, which some people look at this reverse HLS inequality, and they were able to prove even the sharp constant of that inequality. Again, why is that important for us? Because again, it gives you a relation between the two terms in the free energy, and it will allow you to make an argument about being this bounded below or not. Okay? So what we were able to do, in fact, is to generalize that reverse HLS inequality and to show, in fact, that you can have these kind of inequalities, which are written in the way in which we like it better for estimating the free energy, relating again the LM kind of in the integral row to the M, the L1 norm of the density, and this one. And you have that this inequality holds if and only if, and that's the relation that we got, M is larger than D plus D over plus K, D over D plus K, which has nothing to do, in fact, with this relation here. And what happens, in fact, and this is the diagram now, for M less than 1 and K positive, is that this curve, M equals D over D plus K, for which we prove that above that curve we have the reverse HLS inequality. Then at precisely K equals 0, at this point, the line M equals 1 minus K over D is tangent. Okay, so what happens as soon as you cross for M less than 1 or K positive is that this line doesn't play any role. And the reason why this line doesn't play any role is, in fact, that we prove the if and only if. So in fact, but I don't know if it's written there. Okay, we prove the if and only if for the reverse HLS inequality. But what's the implication of this? In fact, what you can show is that the free energy is bounded below if and only if M is larger than D plus D over D plus K. In fact, you can show that for M less or equal than D over D plus K, the infimum of the free energy is minus infinity. So that's what it tells you that that curve over here is sharp for the purposes that we wanted. So yeah, that's precisely what I said over here. Below that curve, the free energy is not bounded below. Between that curve and m equals 1, you have the reverse HLS inequality. This line, m equals 2d over 2d plus k, that is in red, this curve, is the one family of reverse HLS inequality that was present in the literature before our work, and which is in a couple of works of these researchers. And finally, yes, I'm talking about the boring case when I'm slightly than 1. So in fact, these reverse HLS inequalities are in a paper in collaboration with Matthias Delgadino, Jan Dolbo, Rupert Frank, and Franka Hoffman, and appeared some years ago. Okay, so, but, okay, with this, at least we know that this is bounded below, but the question is the minimizer, I mean, is the infimum achieved? Because it could happen that the infimum is not achieved, like in some other cases that I told you before. Is the infimum achieved, and what is the properties that we can say about the global minimizers? So that's the second part of the theorem that we were able to show. So, in fact, what we have to do in order to prove that there is a global minimizer, we had to extend the set in which we were looking for the minimizer. So in fact, we can prove that we have global minimizers over the set of probability measures plus a Dirac at 0. So what we were able to show is there is a global minimizer, and the global minimizer is going to be a radial function, rho star, plus possibly a Dirac at 0. And I say possibly because the only thing that we could say is that we have a minimizer in that set with m star between 0 and 1, possibly 0. Okay? And what we were able to show on top is the following. And it's good to come back to the figure again. Wherever it's dark gray, we were able to show that the m star is 0. So in all these regions, which are colored with the dark gray color, then there we can prove that the m star is 0. So there is no concentration. Now you understand probably the title of my talk, why I call it partial concentration, because I could have a partial concentration of the minimizer at a Dirac at 0. But in the dark gray region, we proved that in fact this doesn't happen. So for those of you that know a little bit about the theory of fast diffusion, this above the blue line is the name is d minus 2 over d. That plays an important role in fast diffusion because above that line, you don't have you have conservation of mass. Below that line, you can lose conservation of mass in the evolution problem. But even if I'm not talking about the evolution problem, it also plays a role for the minimization here. And we were able, in fact, to prove that. And the question that remains is, does the concentration happen or not? Do we have any example where m star is positive? It's really true that we can have something with a little bit of mass at the origin. So that's the open problem that we left in that paper, and that's where the last part of my talk I'm going to concentrate to tell you some new things and how we look at that problem. Okay, so concentration of minimizers. Yeah, so well, I mean, I will not be talking about this if we didn't prove that some concentration does happen. So yes, it happens, but let me explain you what we know, because it's very little still about it. So first of all, if you write the Euler Lagrange conditions for the absolutely continuous part of the minimizer for rho star, you can do perturbations in order to obtain the corresponding Euler Lagrange conditions as in other cases of these type of free energies with interaction energy, with interaction potential. And what you get for the continuous part is this relation. So essentially what you are saying, normally what you will get is that the free energy has to be constant on its support and larger or equal outside the support. Now, since you have the absolute continuous part and the Dirac, then you have an extra term. That's the extra term that you get. So what you get is this, the L, that's for you to see the relation here. In this case, the variation of the free energy is exactly m over n minus 1 brought to the n to 1 plus u from both with rho. Okay. So essentially what you are saying is modulo this minus this is the variation of the free energy has to be constant, but you have these terms that comes from the fact that you have the Dirac part. Anyhow, what you have is this relation that this whole thing has to be satisfied plus L, which is a constant that you can identify in terms of the value at zero of rho star. By the way, I already mentioned it probably in passing before, but you can always prove that the rho star is radially decreasing by the standard decreasing rearrangement. So you know that it's radially decreasing, possibly rho star at zero is plus infinity. But this makes perfect sense because if rho star at zero is plus infinity, since n is less than 1, that would be just 0. That's why I'm saying that rho n is larger or equal than 0. And the constraint that you have also is that the integral of the absolutely continuous part plus the part of the mass of the Dirac has to be 1. Here I normalizing the total thing. Okay? So, in fact, if we want to show if there is concentration, the first thing would be, okay, let's look at all the candidates that solve the Euler Lagrange condition and see if we can get candidates that solve the Euler Lagrange condition with a concentrated part. So that's what we try. And also, if they have to satisfy this relation, let's choose the easiest case in which we can do something more explicit. Okay, k equals 2 is not allowed, I mean, it's not interesting because it's too trivial. Okay, believe me, k equals 2 is just a trivial and you never have concentration. So why I'm talking about k equals 2? Because it looks like a good idea to take even integers to check first. Because what we did is, okay, let's look at k equals 4. Why? You can expand this in terms of lower order polynomials and use the fact that rho star is radial to simplify. So in fact, if for k equals 4, this thing is equivalent to this relation. So rho star, in fact, should be of that form. Should be just rho star to the n minus 1 modulo constant, should be this fourth order polynomial where there are no third or first order terms, and the second term, the coefficient, has to be related to a second moment of itself. We have this nonlinear relation. Plus L, which is what it was already before, that also depends on the rho star. So the question is, can we show that functions that satisfy this condition and those constraints in some range have a concentrated, have a concentrated part? How can I see that they have a concentrated part? Essentially, what I need to show is that the integral rho star is extremely less than 1. If I show that the integral rho star is extremely less than 1, it's the same as to say that the rest is going to be in the Dirac, because I know the minimizer is going to be of that form. So the question is, can I find then rho stars that have an interval less than 1 and satisfy all these constraints. Good. So the answer to that is that yes, that's true. And you know, we were very optimistic. We said that we can find the critical M for 4. We haven't been able to do for any other K already tell you, but we can discuss about that later. But we can find the critical M for K equals 4, which is this number, meaning that if dimension is less or equal than 5, then M star is 0, so meaning that the interval rho is 1. So I don't find concentration, but as soon as the dimension is larger or equal than 6, then this number is allowed. I mean, in the sense, this number, when M is less than MD over 4 is not trivial, it's not empty, compared to M, compared to D over M plus D. And then the mass of the Dirac part is just the difference, it gives you that. And in fact, you are over that number, then M star is 0. So we find the critical M with that little, so it's like to say, let me go back here, probably again, it's nice to see here. So you have K equals 4, let's say here. So I would say in the vertical line here, I can identify an M that is over here. I will tell you that if you are in this range, then you have a Dirac part, but if you are already in that range, you don't. And that's for dimension larger or equal than 6. Okay, so, and in fact, in all those cases where you have a concentration, when M star is positive, then L is 0, and rho star is, in fact, has a singularity at 0 that is integral. And you can check that the rho star has to be that, and that interval is less than 1. That range. Okay, so how we prove it? I mean, as I said, this is simply looking at the Euler-Lagrange equation and trying to find all possible solutions of the Euler-Lagrange equation. In that particular case with K equals 4, we have these two coefficients, B and L, that they have to satisfy these relations. So what we do is to parameterize everything. So let me give you an idea of the proof. The minutes left. So first of all, we parameterize. So as I said, we have 2 parameters and 2 constraints. We have the interval rho plus M equals to 1. So because of that, we can identify B as a function of L. Okay, so this is a kind of an implicit function theorem in which we can show that there is a function B as a function of L, which is differentiable, in which you can write the solutions of the Euler-Lagrange equation in this way, such a way that BL satisfies this constraint. That the BL is the second moment modulo constant of the rho L. Okay? So this is the first step. The second step that we do is now that we have reduced to 1 parameter, which is L, then I look at the mass of the rho L, which remember is the candidate to be the absolutely continuous part of the minimizer. And we prove that it's a continuous and strictly decreasing function with respect to L that converges to 0 when L goes to infinity. I will show you, I put it in red because that's essentially the crucial thing. And I will explain you in the next slide how to prove this. Because now, once you know that, you can see already what is the strategy. What's the strategy? I had 2 parameters, B and L. I chose B as a function of L. Then I have all the candidates, all the Euler-Lagrange, the candidates for the Euler-Lagrange conditions are parameterized in terms of 1 scalar. And then I look at the mass. So the only and this is decreasing and converging to 0. So the only thing I need to know is if this crosses 1 or not. Because if, for instance, and since it's decreasing, in fact, it depends on the value at 0. And it's saying it's continuous and slowly decreasing. So if M of 0 is larger than 1, for sure I will cross 1. But if M of 0 is less than 1, I cannot cross one. So essentially, that's how you find your critical value. So M at 0, you can compute it, and it gives you the value that I had before. So essentially, that gives you the relation. M0, the mass of this is less or equal than 1, if and only if you are below this magic number. Okay?
Sorry.
Yes.
For this kind of construction, how do we guarantee the rho is positive for every x?
Is by the construction, the form of the rho. The form of the rho is telling you that it's positive already.
Do we know the specific form of B?
Yes, because of the Euler-Lagrange condition. Yeah, well, I mean, let me go back here. In the Euler-Lagrange condition already, you could see it. Yeah. This thing is equivalent to that when you span. So that then, and the B is given by the second moment. So all of this is positive.
The B is given by the second moment, it's assuming rho is positive. Otherwise, it's not probability density.
Right, but you are anyhow minimizing over the set of probability measures. So you are looking at the candidates that are positive. It doesn't make sense. But nevertheless, if you span here, this is what you get. It will, is this expression. Is not, you're not, for that, you're not assuming that rho is positive or not. You're just expanding the modulus of x to the 4 in terms of, but nevertheless, from the minimization part, we knew that is a positive density from the systems. Okay, so where I was here. Okay, so I hope to have convinced you that then if you are able to show this crucial part in red, then it amounts to this, and this is how we found this critical M in this case. And to tell you the truth, to prove that that's true, that the M, the mass, depending on L, is extremely decreasing, is easy. It's not that difficult. You just write the stuff in radial coordinates. You know the mean answer is radial. So your, I mean, this is just a notation to simplify this expression. So this is like all the interim in radial coordinates corresponding to the absolutely continuous part of the minimizer. And if you compute the derivative, believe me, that's the formula you get. And really, there's nothing to do here rather than a Cauchy-Schwarz inequality. Because you have to relate these three things, and it's only a factor of R squared that is in between. So you realize that by doing Cauchy-Schwarz in that way, then you get this condition that gives you that is negative. So at the end, in this particular case, that's quite easy. Good. So yeah. Yeah, finally, I want just let me just make a comment about uniqueness also, or if you want, yes, uniqueness. In this case, because everything is so explicit, in the case of with the power 4, when you span, believe me, the free energy can be written also in that way. You span the power 4 in terms of the power 4, the power 2, just that rho is radial. And for radial rho's, this is the expression. And that's the thing that you want to minimize, in fact. And then, just because of the explicit expression, you can see that the difference between the free energy and the free energy of the candidate that I find on satisfying the Euler-Lagrange condition, a general candidate that satisfies the Euler-Lagrange condition, has to be equal to that expression after working at it. Here you just use the Euler-Lagrange conditions for rho star and that the integral of rho star plus m star is 1. And after some computations, you realize that you can write it in terms of that. L star is the Lagrange multiplier associated to this guy. So then, when you see that, okay, from here, everything it has essentially a sign. Why? Because this one has a sign because of the convexity of -1/1 minus m rho to the n. That gives you that this last term has a sign, larger or equal than 0. This is obviously larger or equal than 0, the second term. And the first term, you see, if the integral rho star is equal to the integral rho, this is 0. If the integral rho star is strictly less than the integral of rho, which could be the case in which there is no absolute here, the m is 0. So then, if the integral rho star is strictly less than 1, this could be positive. So the only way in which then this is always larger or equal than 0 is that L star is 0. So this is another way to see that, in fact, that was the condition that L star has to be 0. It's playing a role, and also gives you another proof of that this is the minima exactly, the one that we just found. This explicit relation. Finally, what happens if k is not 4? Okay, so you could think, what happens if there is an even integral? You could use the same idea. Just span in terms of lower order powers, using polar coordinates again for radial functions, but the problem is that you have plenty of more parameters than 2. And now it's no longer first. It's not easy to see how to apply a kind of implicit function theorem in terms of which parameters. And second, is difficult to find how to obtain that the mass, depending on L, that is the same strategy as before, is an increasing function. So we don't know how to prove that. But numerically, it seems that that's exactly what is going on. That the mass as a function of L is a decreasing function, and again, when m of L is less than 1, you would expect to have concentration, and m of L larger than 1, then no concentration will m at 0, sorry, larger than 1, it will not happen the concentration. So these figures try to say that. Let me just explain you a little bit the figures because they are done in a different kind of different values. This for k equals 4, 6, 8, and 10. The x-axis is not m, but is alpha. Is this term, is this expression? Why we choose this one? Because then the curves that the m over m plus k, the curve that divides the different cases of the bounded from below the free energy or not, becomes a straight line in this variable. So it doesn't really matter, but the important thing is each of these curves corresponds to the dimensions. So the blue is dimension 3, 4, 5, 6, 7. And the question that is important is when it crosses 1 with respect to negative values of alpha. Okay? So if the point in which it crosses 1 is in the negative values of, alpha less than 1 value, so in this part, then it means that it's equivalent to say that m at 0 is less than 1. So you see in this for k equals 4, you can see that the first dimension in which this happened is 6, already for dimension 5. The crossing here with this, the horizontal line is to the right of alpha equals 1. And if you increase for k equals 6, you see already that this happens for dimension 4, not for dimension 3. And k equals 8 is this figure doesn't tell you really what happens. You have to do a zoom. When you do a zoom, you miss it. Still is on the other side. But for k equals 10, it seems that in 3 dimensions you will have it. So, so in fact, it seems concentrations are there in some ranges for all the dimensions, but we don't know how to make this well, I would say this is kind of computer-assisted proof in that case, in this case of the 12, to make it a full proof of the problem. And certainly we don't know what happens in the general case of any K. So let me just conclude. So I hope to have convinced you that in terms of minimizers, you can have different regimes. And this relation between the homogeneous pressure and the homogeneous kernels that are clear in the case of degenerate diffusions. There, the dichotomy is very similar to the classical Keller-Siegel model, but for the diffusions, the fast diffusion is completely different. It is related to this reverse HLS inequality, and we have this partial concentration of the mass in some particular ranges. So, and just I want to conclude by saying that we are looking at now at the evolution problem, which is a very natural question that you may have. We just finished with a PhD student of mine a few days ago. We put it in archive. Proof that we can see that concentration in infinite time for the evolution problem. So in fact, we can show that radial solutions of the evolution problem, in the case in which you are with concentration, will show that concentration as t goes to infinity. So it's an unstable phenomenon for the evolution. And I just want to thank my co-authors in some of the papers I mentioned along the way, which are all listed there. And mainly today I talked about these two works, the one related to the minimization of the energy for fast diffusion. Thank you very much.
Very much. Any questions?
I just,
Okay.
I just curious, when you have periodic boundary conditions, we can
Repeat again?
when you have periodic boundary conditions, do you have similar conclusion or?
Oh.
I mean, it's more 50% happening in periodic on torus or something, right? Because experiments can be done that way.
Sure. I haven't thought about periodic boundary condition with the fast diffusion. So I don't know.
Yeah, because
Maybe
I see those people who do chemotaxis experiments, they run a torus, chemotaxis just run on set up test. So usually when they have come to the periodic boundary condition, they get the right model. Instead of because it's really hard to do a really large experiments.
I mean, let me say that with my experience with periodic boundary condition, which is about a related problem, which is for steady state of bifurcation branches, it has a lot of influence. It changes quite a lot the answer. So with periodic boundary conditions, I don't know what to tell you about the partial mass concentration. I will have to think about it. I can tell you that in bounded domains, on a bounded ball with no flux boundary condition, this doesn't change. You still have the partial mass.
Yeah, because you have a kind of like absorption boundary.
Yeah. But with periodic, I will have to think about it.
I think my question was very similar because I was thinking of electrons on the surface of the sphere. So they will be also periodic.
You mean like
the Thomson problem.
yeah, the Thomson problem, no?
Have you done any work on that or?
No, I haven't thought about that on periodic. No.
So as we see in the case of homogeneous U, you can do explicit. What about?
Well, I mean, only with the even integers. I mean, none of that explicit.
Yeah. So how much of this can you do if U is like radial with some growth conditions?
Yeah, well,
homogeneous?
it depends on which questions you're asking. No, for instance, I mentioned in passing about the diffusion dominated regime in which you can prove always that there are global minimizers. That result is much more general than for these homogeneous non-linearities or homogeneous kernels. You can prove it for a very general attractive potential, strictly attractive potential versus a very general nonlinear diffusion. The partial mass concentration, again, this particular phenomena, I'm not sure. I would say it's going to be, I would bet that it's going to be stable under certain assumptions on the behavior of the nonlinear diffusion at zero, probably similar to the fast diffusion. And then later on, probably it's not that important. But yeah, that's for the time being what we know. I wouldn't say that it's an easy generalization. Okay, so it's an interesting problem.
I feel like that.
So for the question, which is, so when you're talking about the evolution problem, what you've shown is that partial mass concentration can occur, but you haven't yet shown that it converges to these steady states. Or
Yes.
You showed that this is what it
Yes.
converges to globally.
As
Okay,
it goes
okay,
to
okay,
infinity.
okay.
So in infinite time,
yeah.
you concentrate and it converges to this profile.
Yeah, these unique, okay, great, yeah, that was.
Well, I mean, this kind of profiles, because we do it slightly for different cases, but yeah, I mean, essentially you do this kind of profile. You have partial mass concentrated at zero, and the rest is a distribution that satisfies the Euler-Lagrange conditions like this, under certain assumptions. We also do it with a standard potential to simplify and do some computations in that paper. That is not listed here, it's a few days ago. Yeah.
Any other questions? Yes.
So, I'm curious to know, for example, with this energy that you have there, is it possible to show something like a Palesmel type of condition?
Palesmel.
Yeah.
Yeah, well, I never thought in terms of Palesmel here because since I don't have any first order, so I never thought about it like this.
Right, I was wondering if the condition of the derivative might prevent concentration or something.
Never thought about it. No, it just it's for me that technique immediately comes with first order functional, so they never thought about trying.
Derivatives.
Right. So that's why.
I was just wondering, I mean, I can prove tightness.
I mean, tightness here in this particular case, when you are in the fast diffusion, it's easy because you have this kind of term that is growing. Okay, so it's not that difficult to see that you have tightness for measures.
Yeah.
That's why you're going to have then and you can apply radial diffusion intervention. So that's why it's easy to prove that you have minimizers on the radial functions plus a Dirac at zero. That's precisely why it's easy in the fast diffusion. K positive. Yes. Yeah, I don't know.
Does concentration in theoretical, can we explain the meaning of that or some phenomena?
Well, I mean, you know, if you go to the fast diffusion regime with the K positive, it's more a mathematical question than an application in a math biology problem. Because then typically the math biology problem for chemotaxis is really Newtonian in any dimension, which corresponds then to the M larger than 1. So I don't know. So what I mean is I don't know any application directly which I can say that equation is interesting physically for some reason. Nevertheless, what I find it very interesting is the atomic problem in which you can see that here you can have partial mass concentration. Like for instance, like if you put it like in comparison to most Einstein problems and things like that, then here you can prove that with a parabolic equation that you have a minimizer has a Dirac part for sure. But yeah, I haven't tried to think about if some of these ideas work for Einstein condensates, for instance, things like that, which is also a natural question that is not too far in some simplified problems.
Yeah, because we have this recursion and it doesn't make sense to me right away that something can concentrate. So I just want to,
Yeah.
okay, yeah. It's non-physical.
Well, I mean, I would say it's just I don't have an application for that particular range.
And the,
That's what I mean.
notice that the repulsion depends, like when rho is really big and m is less than one,
Yeah, okay.
it's not diffusing as fast.
Yeah, so this is it's a good point. What Katie is saying is that, let me put it in that way. Let's look at the Laplace rho to the m term and write it like this. Okay. So then, when the density is small, this is diffusing very fast, but when the density is large, diffusing very little. So the name of fast diffusion, in fact, is a bad name.
Well, it's good when the density is small.
It's not only when the density is small. Yeah, I mean, I think it's a bad name because precisely it's very slow when rho is large, and that's the issue. In fact, Brazil years ago, at the beginning of the 80s, already proved with Freeman that for the fast diffusion equation alone, the Diracs are sort of stationary solutions if you are below E minus 2 over D. In the sense that you cannot get the Diracs approximated. If you approximate the Dirac, then immediately you go. And you cannot get the Diracs, say, from L1 solutions. So in any case, say the Diracs are like sort of the stationary solutions for the fast diffusion. You can think about it like this in some very weird sense. Thank you.
Okay, one